Kasm Workspaces supports a number of deployment architectures to meet your needs. You can run everything on a single server virtual machine with all the Kasm containers and services running on one host. Or you can even move on to a multi-server deployment where individual Kasm roles are broken out across separate virtual machines so you can scale up each service independently, which includes web apps, connection proxies, agents, and even Windows servers. You can go all the way up to multi-region environments that span multiple cloud regions, multiple clouds, or even self-hosted environments. New in version 1.19 of Kasm is the officially supported Helm chart and Kasm Kubernetes deployment architecture. It provides declarative configuration, repeatable deployments, rolling upgrades, and horizontal scaling of individual services, from APIs to proxies to managers, and so on. So you can fine-tune your Kasm deployment to your specific needs. You can track updates to our Helm chart in our Kasm Helm GitHub repo, and you can also install it directly from our Helm repository at helm.kasm.com. You'll find links to both in the description below. Running Kasm on Kubernetes brings with it all the benefits of running production workloads in Kubernetes, especially for environments that are already leveraging Kubernetes for those workloads. You get self-healing workloads, declarative and version-controlled configuration, a values YAML you can store in version control like Git, and even rolling upgrades. Even database upgrade workflows are built into the Helm chart and are part of the default deployment. Individual services such as the API services or the manager services can be scaled to meet growing requirements. When you're considering deploying Kasm into Kubernetes, there are a few prerequisites to keep in mind. You'll need a Kubernetes cluster running version 1.24 or higher. It may work fine on older clusters, but 1.24 and up is what the chart was designed around and tested against. You'll also need Helm 3.18 or higher. Again, it may work with older versions of Helm, but 3.18 and up is what has been validated and is a supported architecture for deploying Kasm on Kubernetes. Beyond that, you'll need a default storage class or a storage class name to pass in for your Postgres database storage. You'll need a domain name, whether that is internal or external, associated with your public address. And you'll also need a TLS certificate to associate with the Kasm proxy services. There are also some additional advantages you can get by leveraging Kubernetes. Things like cloud-native Postgres operator running outside of Kasm that can offer a highly available Postgres database. External DNS, a Kubernetes native service that can manage your public DNS records. Or Cert Manager, which can manage Let's Encrypt certificates for your environment automatically. These are all services outside of Kasm, but if they are already part of your production workloads, they can be leveraged as part of your Kasm and VDI infrastructure as well. There are a number of settings you can modify as part of a Kasm deployment using Helm. Let me highlight a few of the most important ones. One of the most important decisions you'll make is the database used for your Kasm deployment. By default, the Kasm Helm chart deploys a Kubernetes stateful set that manages a single database pod with a storage backend. However, if you have administrative requirements or you need to expand your Kasm deployment beyond a small or a medium environment, we strongly recommend using your own self-hosted or standalone database. That's easily managed through the Helm chart. You set the standalone value to true and reference the external host name or the read-write URL of your database. The next major decision is the deployment size. We've provided a simple deployment size value that can be set to small, medium, or large. This determines the amount of CPU and memory, as well as the number of replicas allocated to the Kasm proxies, API services, managers, Guacamole, the RDP gateway, and the RDP HTTPS gateway services. Keep in mind that the database will always be a single pod within a stateful set if you're using the Kasm managed database, though you can scale a cloud-hosted database to meet your requirements if you choose to. And any of the small, medium, or large size values can be overridden on a per component basis, so you can meet specific service level requirements or cluster constraints. When it comes to exposing Kasm externally, the public address is the URL used to interact with your environment. At a minimum, you will need to configure the proxy service. This proxy service can be a load balancer, a cluster IP, or a node port service. Node port and load balancer are externally accessible. Cluster IP is only accessible internally. If you're using an ingress or an OpenShift route to access Kasm, then this value must be set to the cluster IP so that the service is used internally as the backend for your ingress or route. For multi-zone deployments, Kasm supports a structure called a zone. Zones map to individual Kasm shards, whether that be geographic or logical separation of resources that users can select when they access Kasm. You can use the zone configuration to seed Kasm with specific zones as your deployment requires. For each zone defined in the list, a series of resources is deployed, and the deployment size determines how many resources are deployed within each zone in that region. Any additional resources, such as the guacamole, the RDP gateway, the RDP HTTPS gateway, or Windows and Linux service, will need to be deployed by the administrator after your Kasm deployment is complete. Speaking of those connection proxy services, each one can be enabled or disabled based on your requirements. If your environment is only going to leverage Kasm agents for container-based sessions, you can set each of these services to false. Apache Guacamole, the RDP gateway, and the RDP HTTPS gateway can all be marked as false to conserve resources, both from a Kasm management perspective and a cluster management perspective. If you will be using them, you can turn them on individually or as a group to enable RDP or server connections. Certificate management is a requirement for accessing Kasm. If you are a home lab or a self-hosted user with a special CA or a special certificate lifecycle requirements, you can generate the certificate, add it as a secret in your cluster, and then simply reference the secret name under the certificate value. Otherwise, you can let Cert Manager handle certificate lifecycle directly. By configuring this value and the additional settings below it, Cert Manager will work with any ACME compatible issuer, such as Let's Encrypt, to provision and maintain certificates for your Kasm deployment. Kasm has also taken great pains to ensure the highest level of port security for your environment. By enabling the Apply Security setting, the maximum level of port security is enforced across your cluster resources, such as read-only root file systems, no ports running as root, and all capabilities dropped except those absolutely necessary. This is applied across all of your infrastructure. If these aren't concerns for your deployment, or if you have specialized requirements, you can set that value to false and configure the security appropriately yourself. The final thing to consider is your day 2 operations. The initialize value needs to be set to true for an initial deployment. But once the system is deployed and you need to upgrade to the latest Kasm version, you don't want to reinitialize. Instead, you set the upgrade flag to true and then run your Helm upgrade, and ensure your Kasm version is upgraded along with the chart version, without reinitializing and potentially deleting your existing users or configuration data. There's also a setting for skipping backup and restore. By default, the upgrade includes a database backup and restore step. A PVC is created, and a backup job is spun up to ensure you have the latest data before any database or schema changes are made. One important caveat is that this backup step is only supported with a standalone database. Setting it to true with the bundled in-chart database will cause the job to fail. But if you have an external database and you already manage your own backup lifecycle, you can choose to skip this step. There are many more settings and configuration values available for this Helm chart. We just want to highlight a few of them to help you understand your options when deploying on Kubernetes. Kubernetes Helm charts have 2 version values, and Kasm leverages both to help administrators ensure that the version of the chart that they're using lines up with the version of Kasm they have deployed. The chart's app version is associated with the Kasm bundle release version, while the chart version value is associated with the chart-specific version. You'll notice that the middle number in the chart version corresponds to the Kasm application version that has been bundled and released. For example, chat version 1.1190 corresponds to Kasm 1.19. This is one way administrators can ensure they're deploying the right chart for the version of Kasm that they are authorized to run. To add the chart and install it, you can pull it from our public repository. Run helm, repo, add Kasm, and then helm.kasm.com. And then run a Helm repo update. To list the available versions, use the Helm search option. This shows the version of the Kasm Helm chart that have been released and are available. If you want to work with the latest development versions, you can add the --devel option to print and pull the development builds. So you can experiment with the bleeding edge of both Kasm and the Kasm Helm chart. Another option for deploying the chart, aside from a standard install from the Helm repo, is to use the OCI registry. And that URL is OCI registry1.docker.io/kasmweb/kasmhelm. You can run a Helm install with your installation name, reference the OCI registry, and then either reference a values file or use the set option to specify particular values for your environment, whichever option works best for you. When it comes to running a Helm upgrade against an existing Kasm deployment, remember what we mentioned in the values reference. To run an upgrade, you must ensure that the initialize is set to false and the upgrade is set to true. Having both of these values set to true will cause the chart to fail immediately. And that's a hard failure by design. Once those two values are swapped and any additional values are configured for your environment, you can run the Helm upgrade command and the chart will automatically handle launching the necessary jobs and configuring the necessary resources. One thing to ensure when running your upgrade is that you have a backup storage class configured, so you can tell Kasm where to store the backup. The current process is to spin up a backup job first and then take a backup of the existing database, so that in the event of data corruption during the upgrade, you have an easy rollback path. And for externally managed databases, as we referenced earlier, you can use the skip backup and restore option, assuming you already have your own database backup and lifecycle policies in place. Once those values are configured correctly, you can use the simple Helm upgrade command to bring your environment up to the latest version of both Kasm and the Helm chart. In this section, I'll walk you through a deployment using the Helm chart into an RKE2 cluster. This right here is a 3-node cluster deployed in Oracle Cloud, set up and built out manually. As you can see, we have our 3 nodes, a manager and 2 workers. We've already added our Helm chart, so if I do a Helm repo list and a Helm search, you can see we have the latest chart versions already available. From here, we need to look at the values we'll configure to deploy the chart. An easy way to review them is to run a Helm show values against the repo. This prints every value available, which is a long list, so we'll pipe that to less to make it easier to read. You can see all the different values available for this chart. We could directly edit it from here, but instead, we'll create our own YAML file to configure just the settings we need. You can also specify these values directly using the set option. To demonstrate how few values actually need to be set, we have a minimum YAML file configured here for this demo. You need the public address, which is some URL that you're going to host it at, whether that's an internal home lab address or a public domain name that you own. And you also need a certificate. That certificate can be self-signed, or it can be a trusted certificate from Let's Encrypt or another cloud provider. The certificate provided as a secret is all you need. So if you self-generate the certificate, you add it as a secret into the namespace where you're deploying Kasm, set the public address, and that's really the absolute minimum required to deploy to the cluster. We do have a few additional settings on this one. In our values.yaml file, we've configured our public URL. We're going with a small deployment just to keep it quick and easy. We're also using a load balancer proxy service, And for the certificate, we're going to let Cert Manager maintain it for us. You'll also notice some annotations up here on the proxy service. These set up the load balancer and configure DNS for us automatically through our cloud provider, which is Oracle Cloud. If you look at our public DNS zone, you can see there are no DNS records in it at the moment. This is a brand new domain that we set up just for this demo. Because we have set up external DNS on the cluster previously, it will create the DNS records for us automatically. So with that, let's walk through the deployment. I'll clear the screen and run a Helm install. We name the release Kasm, reference our chart with Kasm/Kasm Helm, set the namespace to Kasm, and then tell it to use our values.yaml file. After it runs, you can see a long block of text. This tells us the Helm release name is Kasm, it's in the Kasm namespace, and that the status is deployed. It also gives us our external URL, where we'll be able to access Kasm once it's up, and also the commands to retrieve our admin password to log in. For now, let's watch our pods deploy into the namespace. See each pod coming up. Our database has transitioned into a running state, and we are waiting for its health check to be marked healthy. And there it goes. The database is running. Once the database is up, the database init job kicks off. That's the next thing to appear, the DB init job. This will transition to completed once the job finishes, which then shuts down that pod. The entire process can take several minutes to complete. So we'll speed up the video here so you don't have to watch every state change. One thing worth calling out is that you may see errors on the RDP gateway and the RDP HTTPS gateway during startup. This is expected because the manager pod hasn't started yet. These services go into a crash loop back off and take a little longer to come up while they wait for the manager to be fully online. Please do note that this is normal. Once the manager is online and running, both the RDP gateway and the RDP HTTPS gateway will transition into a running state as well. So all of our pods are now running, and our DB init job has completed. If we now go back to our public domain and refresh, we can see that 2 DNS records have been created as a result of our deployment. External DNS took care of that for us. One is a text record that establishes ownership and marks these records as managed by external DNS. And the other is the actual domain name we deployed Kasm to. You should now be able to navigate to that URL, and you can now see the Kasm login page. Now, remember that the install output gave us a command to retrieve our admin credentials. Another way to get these credentials is to look at the Kasm secrets directly using the kubectl command. If you look at the Kasm secrets, specifically the admin secret, the value is base64 encoded. We copy it, pipe it to base64-d to decode it, and then print out the result. And this right here is our password to log in. The default username is admin@kasm.local, and then we paste the password that we just retrieved, and we are now authenticated into our Kasm environment. Now that Kasm is up and running, we can verify our infrastructure. Under managers, we have one manager registered. Under connection proxies, we have our proxy service, our RDP gateway, and our RDP HTTPS gateway, all running and checking in at regular intervals as we'd expect. Now, while this gets you most of the way to using Kasm, it doesn't get you all the way there. If you notice, when we run kubectl get pods, there is no agent pod. And that's because our agents are designed specifically for Docker. To have an agent that can launch container sessions, you'll need an external virtual machine configured to connect back to your Kasm services, which it can do easily enough using your public URL. For that, you can follow the standard Kasm documentation for deploying an agent role. Alright, now that we have our Kasm installation running in Kubernetes, let's do a quick recap of where we are. If we check our pods on the RKE2 cluster, all of our Kasm pods are in a running state. We validated that earlier by loading the URL we assigned in the Helm chart, which is demo.rke2.kasm.cloud, and confirming the web page actually loads. And we can log in with the admin password we extracted from the Kubernetes secret. When we poke around our infrastructure, we have managers and we have connection proxies. But one thing we don't have is a Docker agent. Kasm requires a Docker agent to launch interactive workspace sessions. This is an important point to understand. A current limitation of the Helm chart and of Kasm as whole is that it cannot launch workspaces directly inside Kubernetes. It requires an external virtual machine to host the agent role. So let's set that up. We'll install the Kasm agent role onto a virtual machine we have running in Oracle Cloud. The first thing we'll do is grab the installer. You can go to kasm.com/downloads to get the download link for the latest Kasm release. And on the agent, we'll download and extract the installer from the download link. You can see here that it extracted to a Kasm release folder. Now for the exact commands, we'll head over to our documentation at docs.kasm.com. Under the installation section, you'll find a multi-server option, and under that, you can find the instructions for installing the agent server role. Here you'll find a series of commands you can copy and paste onto your agent. We have already run the first couple, so the one that we care about is the install command itself. Let me copy it and drop it into a text editor so we can take a look at it more closely. We are running the install script by also passing a few key values. First, we are setting the role to agent, which tells the installer this machine is an agent. Next, the public hostname flag. This is the hostname or the IP address of the agent that Kasm will use to communicate with it. Despite the name public, you can also use a private IP or a private hostname here as long as the agent is resolvable and reachable by the Kasm manager. In my case, I've already assigned an environment variable that holds the private IP address of the agent. Next is the manager hostname. This is your Kasm URL, which is the hostname of your Kasm deployment. In our case, it's demo.rke2.kasm.cloud. This could also be an IP address or an internal service name if your agent can resolve the management service inside Kubernetes, or a private load balancer address if you want to keep the management communication private. The last piece is the manager token. There are two ways to get this token. The first is from the UI. Navigate to Settings, Global, and if you scroll down, you'll find a manager block with a token field. You can copy this value and paste it into your installer. I've already done that and saved it as an environment variable in my shell, so I'll just use that environment variable here. The second way is to pull it from the Kubernetes secret, since the Helm chart creates it as a secret at deployment time. This is very similar to how we extracted the admin password earlier. The secret is named after the release, in our case that's Kasm Secrets, and the manager token lives under the manager token key. So I'll use this kubectl command, which pulls the value out of Kubernetes and also decodes it for us. With all the three values in place, we'll copy our full install command and paste it onto the agent. We are presented with a Kasm end user license agreement and we'll accept it. From here, the installation takes over. It installs Docker and any other prerequisites Kasm needs. Then it installs the Kasm Docker plugins and then downloads and starts the Kasm containers so that the agent service is running. Once that completes, we'll head back to the Kasm and confirm that the agent has checked in and registered. This step can take a few minutes to complete, so we'll let it run. It's also worth calling out that the agent needs network connectivity back to the manager. The agent's IP has to be allowed to reach the manager on port 443. If a firewall or a cloud security group blocks that path, the agent won't be able to check in, so make sure that communication is open before you start. Alright, it looks like the installation is complete. Now let's check Kasm. Under Infrastructure, Docker Agents, we can see our Docker agent has checked in via its private IP address. Last reporting 29 seconds ago, and it is in the running state as expected. One thing you will notice is that the agent starts out disabled. This gives you control over when it begins accepting sessions. We'll go ahead and enable our agent. Now that we have an enabled agent, let's add a workspace so we can launch a container-based session. You can configure everything manually here, or you can add a workspace directly from our registry with a single click. We'll use the registry and we'll add a Chrome workspace. Once I click Install, you can see the status shows installing for the Chrome workspace. Here's what that means. When we check the agent, the only images downloaded so far are the agent and the agent proxy. Our Chrome container image hasn't finished downloading to the agent yet, and that's exactly what installation indicates here. The image is still being pulled onto the agent. If you click over to the Workspaces tab, which is what your standard users will see, you'll notice a small red triangle indicating that the image hasn't been detected on an agent yet. That triangle will clear once the agent has fully downloaded the image. From the admin side, we can keep an eye on the image status, and we can see that it has now completed its download. Remember that the agent health check happens every 30 seconds. So once that next check-in occurs and the agent reports the image is present, the red triangle goes away. And now we can launch a session. There we go. We now have a container session running. And now we have an interactive Chrome container session with Kasm running in Kubernetes and our agent running on a virtual machine. So far, everything we have launched has been a container session running on our Docker agent, but Kasm isn't just limited to containers. It can also broker connections to full servers. So let's build on what we just set up and demonstrate a different kind of connection, an RDP session to a Windows server. Back on our infrastructure, the Docker agent we installed in the last segment is still available. Now let's add a server, which is what lets us demonstrate RDP connections. Go to Infrastructure and then Servers and click Add Server. We'll call this one Windows, and we'll place it in the default zone. For the connection type, we'll choose RDP. And then we enter the IP address and the port that we'll use to reach the machine. For this example, we're going to use static credentials. And we'll also set the maximum number of sessions to 1. And that's really all we need on the Kasm side to add this server. Once it's added, you'll see our Windows server listed with a status of running. It's worth explaining why. Because we added this server without the Kasm desktop service installed on it, there is no service reporting health back to Kasm. So it simply defaults to a running status. But now let's talk a little bit about the Kasm desktop service, because installing it on your Windows server unlocks quite a bit. First, it reports real health and status back to Kasm instead of the server simply defaulting to a running state. So the manager knows when the server is genuinely online and available. Beyond that, it enables file uploads and downloads between the session and the remote desktop. It can also manage local Windows users and their credentials for you. It also lets you run PowerShell scripts automatically on events like session start, session end, and service start. So you can automate setup and teardown around each connection. And it also supports multiple concurrent users on the same Windows system rather than being limited to a single session per server. For this demo, we're keeping it simple with a static server, but for any real deployment, we strongly recommend installing the Kasm desktop service. Setting up the Kasm desktop service is a topic in its own right, so we have a dedicated video that walks through installing it and configuring it. You'll find the link in the description below. To actually connect to this server, we need to add a workspace. Workspaces are the way Kasm presents servers and services to the users. We'll first select the workspace type to server, since this is a server-based workspace, and then we'll call this one Kasm Windows and give it a description saying Windows on Kubernetes. Now we select the Windows server that we just added. For the client options, we'll choose Web Native so that the users can connect straight through their browser. And we'll leave all the other settings at their defaults for now. We'll go ahead and save this workspace. Now we have two workspaces, our Chrome workspace and our Kasm Windows server. A user can simply select the Kasm Windows style and launch a session. And there we go. We have RDP'd right into our Windows machine. We have connected to Windows through Kasm running in RKE2. In this section, we're going to deploy Kasm using the Helm chart into a GKE cluster, which is a Google Kubernetes Engine cluster in Google Cloud. And this time, we're going to use an external Cloud SQL database. The architecture looks like this. We have our GKE cluster with the Kasm deployment running inside it. We'll expose it using an ingress, and as part of the Helm deploy, we'll also use GCP annotations to automatically create a load balancer. So we'll start by showing you that the load balancer doesn't exist, and deploying the chart will create that load balancer resource in the cloud. We also have a Cloud SQL instance that we have deployed separately. Compared to our RKE2 demos, where one used an ingress and the other one exposed the proxy service directly, the biggest difference here is the database. In those deployments, the database was deployed and managed by the Helm chart. Here, we are using a Cloud SQL instance that was deployed independently from the chart, directly in GCP. Now let's look at the resources on GCP. First, we have the Kasm demo VPC. We also have our Kasm PG16 instance, which is a Postgres 16 Cloud SQL instance. Here is its private IP address, and we're going to copy it because we'll need it in the values file for our Helm deployment. And then here is our GKE cluster. This is what we are deploying against. If we look at load balancers, you can see that there are none currently. After the deployment, you'll see the load balancers created as part of the process. So the first thing we'll do is open our values YAML file. Down under the database section, you will see we've marked standalone as true. And under the host name, we are pasting in the private address of our database. This could also have been a registered URL if you had a domain name for it. With AWS RDS, for example, especially for clustered databases, it often creates a read-write URL, and the host name would need to match that read-write endpoint here. There are a couple of things that are unique to this deployment. First, we are setting the proxy service to cluster IP so that we can deploy an ingress in front of it. You'll also notice some annotations here. We have the cloud.google.com/backend config annotation, which establishes the proxy service as the backend service for the load balancer. We also have the GKE frontend config annotation, which references the front-end configuration for the load balancer. We are using the GCE ingress class, and we are setting allow HTTP to false. Just like in our RKE2 deployment, where we used external DNS to configure DNS host names automatically, we'll do the same here, which is allowing external DNS to set up our public address, which is demo.gke.kasm.cloud. And then we'll also have Cert Manager generate our certificates for us. You'll also see down here that we are making sure to initialize the database. Finally, we have extra objects. This value can be a list of strings or a list of objects representing Kubernetes manifests. In this case, we have provided a list of objects, the actual manifests that we want to create, like a GKE frontend config and a backend config. Adding these to the extra objects allows the load balancer resource to be managed with a lifecycle tied to the Helm and Kasm deployment. With those values set, we'll save the configuration and check our Helm setup. We can see that the Kasm Helm chart is already added, and it reports as the latest 1.19 version. Just to be safe, we'll run an update one more time to verify we have the absolute latest 1.19 chart. Alright, so as you can see, we are now connected to our cluster, and we have our GKE resources as well as other resources are available. However, we don't yet have a Kasm namespace. Now, one thing that's specific to using an external database is that in our database configuration, we have a Postgres master user. The master username is Postgres, and the secret is the Cloud SQL master secret that we need to inject. This secret must be pre-created in whatever namespace we are deploying to. We are deploying to a Kasm namespace, so we need a secret named Cloud SQL master with a key of password. So let's create that. First, we create the namespace Kasm. Then we create the secret. We're creating a generic secret named Cloud SQL master in the Kasm namespace, injecting the value from a literal with the key set to password. The password itself comes from an environment variable that was generated by the script that set this up. This gives us the generic secret with Cloud SQL master as the name and password as the key. We can verify it by getting the secret in the Kasm namespace with YAML output. And there's the password key with the base64 encoded value of the password. Now we are ready to deploy. We'll run our Helm install. I'll set the name as Kasm, chart as Kasm/Kasm Helm, namespace as Kasm, and then reference the GKE values file that we just walked through. Press enter, and after a moment, we get our nodes output showing the status as well as the different commands to retrieve different Kasm secrets. Let's watch our pods with the -w flag. The first thing we see is the DB init job coming up and initializing. This job needs to be completed successfully. If this shows an error, that means there was a problem initializing the database and none of the other services will come online because they all require the database to be properly initialized before they start. Here we can see the DB init job completed successfully. The database initialized correctly. With that done, our API has migrated to a running state. We are just waiting on the remaining services now. Once the API reports ready, the manager will come online next, and then the remaining services will start up shortly after. If things seem to be taking longer than you'd expect, you can check the log output on a pod. You'll see the health check messages come through. These are all debug level and not actual errors, so this is expected as everything comes online. Now that everything's coming up, once the proxy is running, we can come over to GCP and watch our load balancer populate. On the backends, you can see that there are 2 new entries that did not exist before. And same as on the front ends, the application load balancer that was just created by the Helm chart. We can check our ingress status as well, and everything's running fine there. If we describe it, we can see the load balancer controller scheduled for sync, our forwarding IP, as well as our forwarding rule. And we can confirm in GCP that the load balancer name associated with our ingress matches the one in our GCP deployment. This demonstrates that the Helm chart, with those annotations and extra objects and the correct cloud permissions, is able to deploy and create the cloud resources necessary for a full implementation. So let's check for our Kasm login page. And there it is. This also verifies that external DNS added the DNS record correctly to reference our load balancer, and everything is in place. Now let's get our admin password. We'll do a get secrets, find our Kasm secrets, and output the YAML. This gives us our base64 encoded admin password. We then decode it, copy the decoded value, and then paste it into the Kasm login page to log in to the admin account. And now we're logged in to Kasm. We can see our default deployment zone, our manager, as well as our connection proxy resources all running within Kubernetes. So that gets everything deployed into Google Cloud. It set up the Google Cloud load balancer, external DNS added our DNS entries, and we have a valid, trusted TLS certificate created by Cert Manager using Let's Encrypt. And we are connected to an external Cloud SQL database managed entirely outside of the Helm chart. That means we can use cloud native backup and restore policies, high availability, and all the other capabilities of the Cloud SQL instance. We inherit all of those benefits by using an external cloud database when deploying Kasm this way. Let's continue with our RKE2 cluster, which we deployed earlier. We successfully deployed Kasm. We validated that by accessing our URL and by confirming that all of our pods are in a running state. Now, let's say we have increased usage requirements. We are running more sessions and we want to scale our Kasm deployment up. To do that, we'll modify the deployment size of the Kasm deployment. In this modified values YAML file that I already have here for this demo, the main thing we changed is the deployment size. We changed it from small to medium. The second thing we changed is the database management. We added the DB management section and set initialize to false. Because we have already initialized the database, we don't want to risk the init job reinitializing it and resetting it to a fresh clean install, which would mean losing any configuration, SSO, workspaces, or other customizations that we have added, just because we want to scale up. Everything else stays the same. We just want to make sure we don't reinitialize the database while we scale up the deployment size. Notice that we are using the Helm upgrade command instead of the Helm install command. This lets us run an upgrade against an existing deployment. When we run it, the output looks very similar to the initial install. Same release name, which is Kasm, same namespace, but Helm now shows revision as 2, meaning that we have run an upgrade. We have a new revision of the same deployment, while all the other data remains largely the same. Let's watch our pods, and you will see a lot happening. The database itself didn't change in size, but the upgrade did cause the database pod to restart because its resource limits changed. Since we are increasing the deployment size, we need to give the database more resources to support the additional workload. As things scale up, you'll notice we now have a second API pod initializing and coming online, and a second manager coming online as well. Most of the pods have transitioned to running. We are waiting on the proxy to finish because it depends on the manager, which in this case is waiting on the API. One thing you'll notice is that the RDP gateway remained a single pod while the others increased from 1 pod to 2. This is expected because currently the RDP gateway is limited to a single pod and does not horizontally scale. Now everything's up and running. It took a little time, but all the pods are now in the running state. Let's look at the resources of one of our API pods. We'll do a kubectl get command to output the actual manifest of the API pod. Under resources, the limits and requests have been slightly increased to support the larger workload, and an additional replica was also added. Our replica count now went to 2, which is why we now have 2 API pods instead of 1. Now let's say we have a specific environment where the proxies are getting hammered. Maybe we're distributing a large number of sessions across various services using Guacamole and RDP thick clients through the proxy, along with a large number of container sessions. We just need to scale up the proxy, scale up Guacamole, and increase our manager resources because the workload is getting heavier. We have options to modify all of those things manually. So let me open the manual scale values.yaml file I already have here for this demo. We have a manual scale option here. Notice we have kept the deployment size at medium, so we are working from a medium baseline. But at the component level, we are going to scale our proxies up to 3, giving us an additional proxy to load balance connections across. We'll do the same with Guacamole, increasing it to a third node, so sessions are now distributed across 3 instead of 2. And for the manager, we don't need additional managers, but we do need to give the ones we already have more resources. So we'll roughly double the manager's CPU and memory to make sure it has all the resources that it may need. To apply this, we'll run another Helm upgrade, this time referencing our manual scale values file. Helm now shows revision 3, which means a third change to this deployment in the Kasm namespace. Watching the pods, you will see the manager kept one pod running and started 2 new ones because we increased its resource requirements. We also got a third proxy deploying. The old managers are being terminated as the new ones transition to running. This is the whole idea behind Kubernetes, rolling updates across your infrastructure in a non-disruptive way. We have also scaled up a new Kasm proxy node. All the pods are now in a running state. We have 2 managers, 3 proxies, and 3 proxy nodes. All the pods are now in a running state. Let's confirm our manager resources were actually increased. We'll get the YAML output and look for the resources. Ignore the init containers here because these are just what come up to make sure the necessary resources are available. But here are the real resources. The limits are set to 1.5 CPUs and 2 gigs of memory, and the requests set to 1 CPU and 1 gig of memory. So our values were applied correctly to the manager pods. And that's how easy it is to scale your environment. Back in the Kasm UI, if we refresh and go into the connection proxies, you'll see a large number of proxies. It looks like one of our RDP gateways didn't deregister itself, and that's not disruptive to Kasm. It's simply been marked as unavailable and it won't be used. So you can easily delete it as part of your infrastructure cleanup from the Kasm UI itself. You'll also notice we have 3 Guacamole nodes along with our RDP gateway and the RDP HTTPS gateway, all up and running. If we check the managers, we have 2 managers running, and we allocated additional resources to them, so they can handle larger workloads and additional capabilities beyond what they could before. And that's how easy it is to scale Kasm and make modifications to your deployment using Helm and Kubernetes. In this section, we're going to look at deploying a multi-zone Kasm configuration with the Helm chart. As we mentioned earlier, and as you will see in this diagram, one of the things that's unique about zones in Kasm is the way the Helm chart handles them. In the primary zone, in this case Kasm Zone A, you'll see all of our services, the API, the manager, and the Nginx proxy, as well as the Guacamole, the RDP gateway, and the RDP HTTPS gateway. However, for secondary zone, which is Kasm Zone B, we only have the proxy service, the API, and the manager service. These are the only services Helm is responsible for deploying in the secondary zone because they communicate directly with the database and need to be in close proximity to it to ensure reduced latency and high-speed operations. If you require any of the additional connection proxy services in a secondary zone, such as Guacamole, the RDP gateway, or the RDP HTTPS gateway, you'll need to deploy those as virtual machines in the region or VPC of that secondary zone. You can see here we have the dedicated proxy and the connection proxy, which handles your RDP services with agents and servers behind it. In your primary zone, it's configured like a standard single zone Kasm deployment, where your agents and servers are virtual machines that communicate directly with the primary zone, Zone A in this case. Let's see how this looks from the Kasm Helm chart perspective. In the values YAML file, we'll open our RKE2 zone values file. In this case, we have changed the domain name. We are using zonedemo.rke2.kasm.cloud. But more specifically, notice the zone configuration. For our Kasm zones, we have Zone A and Zone B, and each has a designated proxy address. These proxy addresses have to be unique URLs used as the proxy address for each zone. They must be unique because they are added as specific route rules on the ingress, or on the OpenShift route if you are using OpenShift. The proxy service type must be set to a cluster IP for a multi-zone configuration. We can't use a load balancer service here because there are multiple routes that require an ingress or route. From there, we have our standard annotations configured for our traffic ingress. All the other configuration settings are set as they should to support this environment. So with that, let's deploy this into Kubernetes and see what happens. We'll deploy it just like before with a Helm install. This time, we'll give it a unique release name called Kasm Zones. We'll reference the Kasm/Kasm Helm chart, and then we'll create a new namespace called Kasm Zones, and then pass the demo RKE2 zones values file that we walked through earlier. We run the install, and we can see our release name and that we are on revision 1. Let's watch our pods. One thing you'll notice, just like in the diagram, is the pod naming. Previously, it was API default. In this case, since we went with a small deployment, meaning one API, one manager, and one proxy per zone, we have an API for Zone A, and an API for Zone B, a manager for Zone A and a manager for Zone B, a proxy for Zone A, and a proxy for Zone B. Each of those services is unique to its own individual zone. Once all the pods come online and we log into Kasm, you'll see 2 managers registered, each under a unique zone name. And we'll actually have 3 zones. I'll explain that when we get there. As you can see, all the pods are now up and running. Notice that on this deployment, we used an ingress instead of a service, which is what we used for many of the others. So here we have our traffic ingress, and you can see all of these host entries are the different URLs that we added for each zone, as well as the main public address, all associated with the ingress IP. On the DNS manager, which is OCI in my case, we should also have all of our public DNS records added. We have our main address, our Zone A URL, our Zone B URL, and they all point to the same IP, which is the same load balancer stack managing all of them. And let's see if Kasm is available. And it is. We'll log in with our default account. Once again, we can get the admin password from the notes output we got from the Helm install command. Just copy the command, paste it, and it prints out the admin password. I can now log in to my default admin account on Kasm. Now let's look under infrastructure. Under managers, you can see our Zone A manager and our Zone B manager. And you can see we assigned Zone A and Zone B as their zone names. All of this is taken care of automatically. Now, one thing you'll notice is under the deployment zones, remember I said we'd have 3 zones. This default zone is created during the default initialization of the database. Since we are doing a multi-zone deployment with Zone A and Zone B, and our resources are directly associated with these zones, the default zone is no longer needed. You can just delete it to clean things up and remove any confusion. Everything else in the connection proxies looks just like a normal deployment, except that instead of default, you will see our Zone A designator telling us which zone each connection proxy resource is associated with. And as with our other demos, we are not deploying agents as part of this. We just want to highlight the resources the Kasm Helm chart itself is responsible for managing. And as you have seen, there's a lot the Helm chart manages for you, and it's tremendously useful in getting Kasm deployed into Kubernetes. And that brings us to the end of this video. We have covered the new Kubernetes deployment architecture introduced in Kasm 1.19, the key configuration options and chart versioning, and full deployments across an RKE2 cluster, a GKE cluster with an external Cloud SQL database, horizontal scaling, and even a multi-zone configuration. With the officially supported Helm chart, you get declarative, repeatable, and scalable Kasm deployments that fit right into your existing Kubernetes workflows. Thanks for watching. You can find links to our Kasm Helm repository, documentation, and any additional resources in the description below. And I'll see you in the next one.